Good afternoon, everyone, and warm welcome to yet another episode of this boot camp. So, as everyone know that from 21st of the June to 21st of the July, Planetarium is having boot camp, and this boot camp has been organized to give you little hands-on and little intensive detailed education related to the various aspects of astronomy and astrophysics. So some of the lectures are kept online so that people who are unable to join offline at the planetarium can get the benefit of the topic we have discussed during the program. So today we are here to discuss something very interesting, and to talk more on this we have with us science communicator Kshitij Pandey, also popularly known as Kshitij. He will be talking today on how Neutrinos sees the world. Kshitij is an astrophysics enthusiast and creative content creator. His content you can also check on his YouTube and Instagram handle, which is under @astro.kshitij. With his interactive content, he is bridging the gap between the intrigue, cosmos, and sharing knowledge with the curious mind. Not only he shared his knowledge through captivating written content, but also he got chance to deliver his lectures and talk in some of the esteemed organizations in past. In 2019, his dedication to physics was recognized when he was awarded with the silver medal at the University of Physics competition organized by Calvin College in Helena, Montana. Again, we'll ask you, urge you, if you are keen to explore the universe and need someone to translate the scientific complexity into engaging narrative or simplify, wants to share a cosmic enthusiasm, do not hesitate to connect with Astro Kshitij. And today, Planetarium is privileged to host you, to share space with you, and to know more about this topic. So over to you, Kshitij. Now we all are ready to explore and travel to the universe.
Hello. So, am I audible now?
Yes, you are audible.
Okay. So, first of all, thank you very much for this wonderful introduction. Let me just set my
Sure,
camera.
sure.
It's
Please. Yes,
having some
yes,
issue.
yes, yes.
Okay. Let me know if it's good because I cannot see right now. Just a minute. Last moment. Okay. Perfect. Yeah. So once again, thank you so much for this lovely introduction, and it's a privilege to speak here for the Nehru Planetarium. I've been in touch with the people who have been working in Nehru Planetarium for a long time now, so it's a great moment for me. And now, not wasting much time talking simply about how neutrinos see the world. And when we say neutrinos, what exactly do we mean? So neutrino means the tiny neutral one, as the name suggests, and they are the particles that are all around us. They are passing through our body. In fact, more than 600 billion of them are passing just through the cross section of our thumb, and yet here we are sitting as if nothing is happening. These tiny ghostly particles, we call them as ghost particles also because they are so hard to detect. They can help us to understand universe from a very different dimension. How? That we are going to understand in the course of this presentation. But let's talk about how do we understand the universe right now. If you see historically, the best way to understand universe is through photons, is through light. In earlier times, when our ancestor used to look at the stars or look at the moon, they knew that it is there. They knew that it was the reality. Why? Because they were able to see that. They were able to see that because of the photons. Obviously, that time they do not have the term for that, which is photon. Today we call it as, or electromagnetic wave, or whatever it is. But that time they knew that something was there because they are able to see it. So light has always been helping us a lot in order to understand the universe. We have, if you ask a 3-year-old kid that how can you say that moon is there, he or she will definitely say, yeah, moon is there because he or she can see the moon. And as the technology advances, we realized one thing, that yes, it's true that electromagnetic wave are good, but there is a certain limitation to it. First of all, we can see only in visible spectrum only. So it was just the matter of technological advancement only that we come up with technology which allows us to see things in a very wide spectrum. So today we can see things in gamma rays, we can see things in X rays, We can see things in visible light, we can see things in infrared, radio waves, and there are a lot of other spectrum that I have not I'm not going to cover because that is not the whole point of presentation today. But the main point is that we can see universe from a very different lights, technically very different lights, and they help us to understand universe in a different way. JWST see it different in a different light regime. We have Chandrayaan X-ray, we have Hubble telescope, and a lot of other telescope which use different wavelength of light in order to understand the universe. And that is something very interesting because each of these spectrum have their own pros and cons. Some of them allows us to see things in more detail, some of them allows us to see farther things away, and there are a lot of things. But again, the problem is that we are still restricting ourselves with the electromagnetic waves, or in technical terms photons only. Is there any other way by which we can see the neutrinos? It's very hard to understand, because when we use the word can we see, the see word itself associate with something we call it as observation, and that observation comes from the photon, from our intuition. But that observation can be of different case, and here I'm going to talk about the neutrinos. So you can see the Milky Way galactic center. This is in the visible regime, and this visible regime you can see in gamma ray and different things. But what I'm going to cover here is the photon, is the neutrino. Sorry, with the neutrinos we can see things in a very different dimensions, in a very different perspective, and that is possible is because neutrinos allows us to see things in a very detailed way. Why? We are going to answer that in the upcoming slides, and how exactly neutrinos are working, what exactly are neutrinos, that we are going to talk about. But let me give you some small introduction about neutrinos. So neutrinos are part of the standard model. There are three types of neutrinos: electron neutrino, muon neutrino, and tau neutrino, which are associated with the electron, muon, and tau. The standard model of particle physics actually tells us how the universe is made up of, what the universe is made up of, the universe that we know of. I'm not talking about dark matter, dark energy, or some other elusive kind of matter, but the universe that we understand, that we see, all of those things are made up of these particles. Higgs is missing here, but more or less these are the particles, and these neutrinos are very amazing particles. So the standard model includes the three flavors of neutrinos, of massless neutral neutrinos, right? In standard model they are massless, because initially when they were proposed they were actually massless. They do not get their mass from Higgs boson or from Higgs mechanism, but they do have mass. So even though standard model says that there is no mass, they do have mass. And how, why, we will understand that later. But one of the most interesting thing about neutrinos is that they only interact with weak nuclear force. That is, they are not going to interact with this photon, gamma. They are not going to interact with this gluon, but this Z and W. We call it as Z boson and W boson. And that Z and W boson is always present inside the nucleus of an atom. Now here's the interesting thing: 99.99999% of the atom is empty space, and nucleus contains a very small amount of volume. That means for the neutrinos, 99.99999%, which is entirely made up of matter. I'm not even talking about the vacuum. I'm talking about something which is totally made up of matter. For them also, 99.99% of the space there is empty, because they are not going to interact with them. It's for that reason we know about alpha rays, beta ray, gamma ray. It is said that gamma ray have the highest penetration, but even if you take 5 centimeter of the carbon thick wall, gamma rays will not be able to penetrate that. But on the other hand, if you take 1 light year thick of lead, I'm talking about lead are very dense. If you take 1 light year of lead and pass, let's say, 100 neutrinos from them, more than 90 neutrinos will come out from the other side. That's the penetration power that we are going to talk about. And that is possible only because they interact with the weak nuclear force, that is W and Z boson. And because of this property, they are called as ghost particles, because it's very hard to detect them. We have to build very large detector in order to find neutrinos, in order to see how neutrinos are working, and they are particularly very bizarre. But anyway, talking about the neutrinos again, so how do we know about these neutrinos? What exactly are these neutrinos? What are the historical implication? So during this presentation, we are going to understand what are neutrinos and why do they matter. How do we detect the undetectable? What can neutrinos? How can neutrinos reshape our understanding of physics? And what does the future hold for neutrino research? I believe that the best way to talk to start a topic is going through the historical background. why neutrinos was introduced, what was the need of it. So there was a very big problem with the beta decay. The problem with the beta decay is that whenever a parent atom is split into a daughter atom as well as an electron, or let's say a positron, the total energy of daughter atom and the electron was not as equal as that of parent atom. This was not only violating the conservation of energy, but it was violating the conservation of momentum, conservation of angular momentum, which is a very, very, very big thing in physics. You can do anything, but you cannot violate these conservation law unless we are talking about in cosmological scale where energy conservation does get violated, but in small scale it should not, right? So the problem is that how is it possible that these neutrinos, sorry, that time neutrinos were not discovered. How is it possible that these beta decay is actually violating the law of conservation of energy and other conservation law? That means either there is something that we don't know of, or there is a new physics involved, and eventually we are talking about new physics only. Why? Because then in 1930, Wolfgang Pauli, who is a very famous theoretical physicist, he said that maybe there is a particle that we are not able to detect, and all the missing energy that we are not able to see is hiding in the form of those tiny particle. Initially he called them as neutron. That time James Chadwick didn't discover the neutron. It was maybe 4 or 5 years after that. But since James Chadwick gave the name neutron and that was very massive, just to avoid confusion, Fermi later termed that neutron, which Pauli said as neutron, into neutrinos. So today we call it as neutrino only. So although Wolfgang Pauli gave the hypothesis of the neutrino, it was Fermi who gave the name of it. Now, it was fitting very well. It was actually explaining all the things. But the problem is that even Pauli was not very much convinced about this neutrino hypothesis. He said in one of his letters that it was his desperate remedy to solve this problem. And then there comes the take of Niels Bohr. Niels Bohr, every one of you know who was Niels Bohr. He was one of the founding member of quantum mechanics. He was a very pioneer scientist, and he had a very strong take when it comes to neutrino. He said that neutrinos should not exist. It was very big blunder which was done by Pauli. In fact, he was so against neutrinos that he even considered that thermodynamics might not be universally applicable. That's a very big statement. If any other person would have said that, scientific community would have been laughing. But it was Niels Bohr. He was very giant at that time. So if he was saying something, so people had to listen. Now, Bohr preferred questioning physical laws over accepting an undetectable particle like neutrino. However, later, in some scintillator, we found the proof of neutrinos, and that time Niels Bohr had to agree that neutrino does exist. But we are not going to talk about how neutrino was discovered first time. But in fact, we are going to lead to something more interesting, and that lead us to the solar neutrinos. So there are two sources of neutrinos. First is natural sources, another is artificial sources. Natural sources like sun is producing neutrinos all the time. We call them as solar neutrinos, and we are going to discuss about them in very great detail here. Then we have astrophysical neutrinos, which comes in the form of cosmic rays, and they hit the atmosphere. They produce a lot of neutrinos. So astrophysical neutrinos, the origin of their parent particle come from very astrophysical phenomena, let's say supernova, maybe active galactic nuclei, quasar, blazar, or it can be anything. There are a lot of things which can produce these astrophysical neutrinos. Then there are artificial sources. There are nuclear reactor by which first time the neutrinos were discovered, that they were proved that neutrino does exist. We have particle accelerator, we have Fermilab, we have large hadron collider which can produce neutrinos. But let's talk about neutrinos that are coming from the sun. We call them as solar neutrinos. So the proton-proton chain occurs around 10 to the power 38 times each second in the core of the sun, which is a very, very large number. That means about 2 into 10 to the power 38 neutrinos escape the sun every second, and every square centimeter of the Earth's surface is being hit by 600 billion neutrinos every second. That is happening because of this PP fusion. You can see this in the slide here, that how so many processes create neutrinos. So because of these, we also call them as CNO cycle. Because of these CNO cycles, we know so how many neutrinos should be coming to us for each centimeter square on Earth. There are some big deal of calculation which are not very tough. They are very simple. So here comes a very interesting story of John Beckel and Ray Davis. So John Beckel was a astrophysicist, and he calculated the total number of neutrino flux should be coming from sun to the earth. And based on that, Ray Davis decided to verify that how many neutrinos are coming from there. So what he did is that this is very famously known as Homestake experiment, which took place in the Homestake gold mine. Inside the gold mine, they used gold mine so that they can protect the overall setup with the cosmic rays and other noises, so that Earth will be working as a filter and they can shield all of their apparatus. Now, Ray Davis was marvel experimentalist. He was a legendary experimentalist. What he did is that he took a large amount of chlorine, and what happened is that whenever a neutrino hit chlorine 37, it convert into argon 37 and also emits an electron. Now, what he was expecting that out of 10 million chlorine atoms, only 10 argon atoms will be converted into only 10 chlorine atom will be converted into argon because of the so less interaction property of the neutrinos. And guess what? Ray Davis was even able to calculate that. This was such a engineering marvel that it requires a talk on itself. If you ever get time, just read how Ray Davis did that. It was such a genius thing. In fact, he was so sure about his experimental prowess that he sometimes used to ask researcher to create the random number of argons in the tank, and he will exactly calculate, very precisely calculate total number of argon atoms that are being created, and he was right all the time. But there comes the problem. When he started to calculate the total number of neutrinos that should be coming from the sun to the earth, he was only getting one third of the neutrinos. And that's a very, very big problem, right? Because why is he getting only one third of the total neutrinos? Where are two-thirds of the neutrinos going on? So he thought that maybe there is some kind of error in his calculation. So he tried to perform that again and again and again for the next 22 years, and he was getting the same result. And not only him, there were so many other like detectors all around the world who that time started to find the neutrinos, and they were getting exact same result. So on the right side you can see this yellow bar which was showing that total number of expected neutrinos should be detected, and the blue line shows the total number of neutrinos that we were actually getting. This was a very big problem, and it was termed as solar neutrino problem. So that was clear that Ray Davis was not doing anything wrong. So it came to John Beckel. Maybe he was doing something wrong with his calculation. John Beckel tried to confirm that calculation, and again he asked many of his colleagues to recheck his calculation. And he said that if all of our understanding about the sun is right, about its temperature, its mass, and other things, then this is going to be the exact number of neutrinos that we should be able to detect. And there is something that we don't know of. And this was the big problem of the solar neutrino problem. And this leads to the Bruno Pontecorvo. Bruno Pontecorvo says that maybe there are some kind of oscillation that are being happening inside in the neutrinos. So it was that time when muon and tau were discovered. Muon and tau are the other particles. They are the higher cousins of electrons. So there is electron, muon, and tau. He said that if there is an electron associated with, he said that if there is a neutrino associated with the electron neutrino, there should be a muon neutrino, there should be a tau neutrino. And he said that there should be an oscillation. He called it as neutrino oscillation. He was the first person who gave that term many years ago. However, he was not able to explain how this oscillation was happening and why are we getting so less result. Unless MSW effect was termed. MSW effect was given by McLeod, Simron, and Wolstein. They were three legendary physicists who suggested that neutrinos can transform into each other much more easily in the presence of matter. So we also call it as matter effect. Now it's very strange. I told you that neutrinos do not interact with this electromagnetic force and other forces. But despite that, if it is going through larger abundance of electron density, the electron neutrinos are going to change its property to muon neutrino and tau neutrino. And that is very disturbing, and that is very strange. So how is it happening? So what was actually happening is that when the sun was producing neutrinos, these solar neutrinos, all the neutrinos were initially electron neutrinos. In fact, our detector was also sensitive to electron neutrinos only. But by the time it was passing the surface of the sun, and it takes very less time for them to pass through the surface of the sun, unlike photons which take millions of years because of the high density. During that time, many of the neutrinos were being converted into muon and tau. And by the time they reached to the earth, they were almost equal number of electron neutrino, muon neutrino, and tau neutrino. And that explains that why there is so much, why we are getting only one third of the result and two third of the neutrinos, which were muon and tau neutrino, they were missing. So that was solving a very big problem. But the problem is that we cannot say it is for sure unless we detect it experimentally, or we somehow see it observationally that yeah, it is being happening. And this happened in 1998. In 1998, Super Kamiokande detector, which is the successor of the Kamiokande detector, it's a very large tank and it looks very beautiful, right? These golden balls, they are photo detector. What are photo detectors? How do they work? We'll explain that. But let's understand for now that this Super Kamiokande detector was able to detect neutrino. So what it did, that is it was actually initially it was made for the proton decay, but then it was also started to calculate the total number of neutrinos. So what Super Kamiokande detector was doing is that they were calculating the total number of neutrinos they were getting above their head, because it was again a underground, it was made in underground mine. All these neutrino detector are always made in underground mine because of obvious reason, they have to eliminate the noises. So they wanted to calculate the total number of neutrinos that was coming above, from above their head, and that was coming from other side of the earth, right? So as I told you, neutrinos have excellent penetration power. So ideally they should be getting that same number of neutrinos, and they were actually talking about astrophysical neutrinos. So considering that earth is spherically symmetric, there should be equal number of neutrinos that are being made from all sides of the earth. So that means if neutrinos have this excellent penetration power, they should be getting equal number of neutrinos from all the side. But it turns out it was not the case. They were getting more number of neutrinos from above their head than they were getting neutrinos that were coming from other side of the earth. And that can only be explained with the help of MSW effect that we just talked about. Now here's a very interesting conclusion that can be drawn here. If neutrinos are shifting their flavors, that means neutrinos are experiencing time. If neutrinos are experiencing time, that means they do have some mass. They are not massless as it was initially predicted by Pauli or other scientists that neutrinos should be massless. This was a very groundbreaking result, and it led to one of the Nobel Prize to Ray Davis and the one of the spokesperson of the Super Kamiokande detector. This was such a big discovery. So Super Kamiokande detector in 1998 proved that MSW effect is taking place, but that was done for the astrophysical neutrinos, not for the solar neutrinos. After some years, that same experiment was performed for the solar neutrinos, and same result was drawn. But Super Kamiokande detector in 1998 changed our understanding about how neutrinos work and how these things work. Now, Super Kamiokande detector is not the only detector we have. There are very other detectors. We also have Fermilab, which is very pioneering in creating neutrinos. Here comes my favorite one, the Ice Cube Neutrino Observatory. It's a very huge, very large neutrino observatory. And I want to dedicate few minutes just to talk about this Ice Cube Neutrino Observatory only, because it's a rather like a very significant thing. And to give you some idea how big it is, this is the Eiffel Tower here. 328-meter is the height of Eiffel Tower. And in total, more than 3 Eiffel Tower can fit inside this Ice Cube Neutrino Observatory. That is the scale I'm talking about. This is 1 kilometer square array of the total phototubes that are being placed here. They are placed in South Pole because there again this process happens which is known as Cherenkov radiation. I'll talk about that. But before that, these Ice Cube Neutrino Observatory are more sensitive to the neutrinos that are coming from the other side of the Earth, as you can see in the left side of the screen, than from the neutrinos that are coming above them. Again, because Earth work as a great filter, they remove all the noises. But how do they work? So before that, let me tell you something about Cherenkov radiation. We know that nothing in the universe can travel faster than the speed of light. Light is the fastest thing. But light can be slowed down in the medium that you must have studied in your school, right? That light gets slowed down in the medium. That means technically inside a medium, a particle can travel faster than the speed of light. It's not going to exceed the speed limit that is 3 into 10 to the power 8 meter per second. But inside that medium, for that photon, it can travel faster than the speed of light. And this leads to a blue cone of light, which is known as Cherenkov radiation. So what this photo detector does here is that they look for those Cherenkov radiation. This Cherenkov radiation will tell that neutrino strike a nucleus, which released an muon or maybe other kind of particle which is traveling faster than the speed of light inside that medium. And by that logic, they are able to see the neutrinos or detect the neutrinos. So this is how this works. This is the large array of these particles, these phototubes, and see this neutrino strike one of the atom, and this create Cherenkov radiation. So by tracking that, we can see that how these neutrinos are like coming from. We can like talk about their direction and a lot of things. This is how Super Kamiokande detector is also working. This is how most of the Cherenkov radiation based detector are working. There's a large array of Cherenkov radiation detector, one in Argentina, other parts of the world. All of them are working on the same principle. Neutrino comes, they hit a nucleus, a particles come out of it which travel faster than the speed of light inside that medium. It creates a blue cone of light. We call it as Cherenkov radiation, and because of that Cherenkov radiation, we try to detect from which direction that neutrino was coming from, what was the energy of that neutrino, and by that logic, we are able to understand about this. Right. Now let's come to neutrino astronomy. I have given you some great detail. What are neutrinos? Why they interact so less? How can we detect them? But what is the use of these neutrinos? What are the advantages? That is the main thing. So remember in the starting, I told you that with the visible light we can see these things, but with the neutrinos we can see something in very great detail. This is known as neutrino astronomy. The problem with the light is that it can easily be deflected, it can easily interfere with the environment. On the other hand, because neutrinos have such a low like interaction property, one great thing about them is that once they carry energy, they take the energy, they do not interact with the environment, they do not interact with anything, but once they do, they give all the information. So unlike photon, which lose its energy in the form of redshift, which lose its information in the form of interaction, hindrance, and all kind of things, photons lose a lot of their energy. They get interacted, there are a lot of things that happen with the photons, which is a very big problem for astrophysicists and astronomer. But none of this happened with the neutrinos. In fact, neutrinos carries 100% of their information, which photons cannot do that. So neutrinos have by far very great advantage, but the only problem is that we cannot calculate them very easily as we can do with the photons. The property which the reason they are such a good source of information is also the reason why we are not able to detect them very easily, because they do not interact with ordinary matter. But that means if we somehow find a way to detect these particles in a very efficient manner, it means that we can understand universe in a better way. And this leads to the neutrino astronomy. Now, this is the image of the sun. And this is not the exact image, this is artistic render. But with the photons, we can see just the surface of the sun, right? I think everyone here agrees that with the photons, what the best thing we can do is see the surface of the sun. But with the neutrinos, we can actually see the core of the sun. I have also talked about this in the previous slide, that photons take millions of years to come out of the surface of the sun, because there are a lot of interaction, there are a lot of hindrance, there are a lot of resistance. But for the neutrinos, these things does not exist. That means if we are detecting solar neutrinos, most of them are the neutrinos which are coming from the core of the sun, and that solves a very big problem, because with the photon we cannot know what's actually inside the core of the sun. Understanding this surface of the sun and what's actually happening inside of them is still a very big mystery, even though sun is very near to us. But the neutrinos can help us to solve that. So neutrinos can help us to understand things which are very far away about the core of those things, which photon can never allow us to do that. One more thing is that for type 2 supernova, so there are a type 1 supernova, then in type 2 also there are different kind of supernova. In type 2 supernova, a star emits 99.9% of its energy in the form of neutrinos. Why that happened? It happens because of the something called as gravitational collapse. If you have seen the movie Oppenheimer, you must have seen that Oppenheimer worked on the collapse of the star, right? That whole thing is known as OSD collapse, named after Oppenheimer, obviously. Snyder was the collaborator of Oppenheimer, and that was an Indian mathematician who was working on that independently, and he discovered that collapse independently, but he was also given this name, so we call it as OSD collapse. But I won't be going too much into this. The main point here is that this collapse says that all the photons will be trapped inside the star. But what will happen that these neutrinos, they are not bound to be trapped. And conservation of energy and other laws of thermodynamics says that any system would want to release its energy as soon as and as much as possible. That means neutrinos are the best way by which they can release their energy. That is why for these type 2 supernova, which later converts into let's say a black hole or maybe a neutron star, 99% of energy come out in the form of neutrinos. And that means that the light that we are seeing is just 1% of the energy. And these neutrinos gives us such a good opportunity to understand the core of star itself. In fact, the neutrinos that we receive from a type 2 supernova reach us before the light. It's a question for all the people who are watching this. What might be the reason? We all know that photon is the fastest thing in the universe. When a supernova is taking place, why on earth we are detecting neutrinos 2 or 3 hours before the photons? Shouldn't it be the other way around? We should be getting the photons and neutrinos. This is a question for you. At the end, I'll answer this question. But meanwhile, you can think that why is it the case? Why is it the case? You can just think about that. Also, considering that you at this point you have to agree with me that we get neutrinos before the photons. That means we can use these neutrinos as the alert system, that if all of our detector, and at this point we have a lot of neutrino detector, our neutrino detector are detecting the neutrinos. That means a supernova has happened, and we can alert all of our big observatory to point in that particular direction, so that they are well prepared about the light that are going to come, and they can take most out of it. So not only it can help us to understand things in a more detailed way, this neutrino at this point of time can also give us the warning of the some of the bigger bizarre things that are going to happen, because these neutrino are going to reach out to us earlier only. So there are a lot of events in the universe that are being facilitated with the help of neutrinos, right? Because these neutrinos are all around us. The reason I'm so obsessed with neutrinos was because in my master's thesis I worked on ultra high energy cosmic rays. So I'll go to that in detail, but before that I'll talk about the ultra high energy cosmic rays, right? So basically we know that there are so many type of supernova, there are so many types of event which can create so much amount of large energy. We also know about large hadron collider. At this point of time, large hadron collider can create a total energy of total collision energy of 10 to the power 14 electron volt, which is very, 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 very high. Like it can evaporate a person. It's such a high energy, 10 to the power 14 electron volt. But the ultra high energy cosmic is that we are detecting can be go in the order of 10 to the power 22 electron volt. That means 15, 16, 17, 18, 19, 20, 21, 22. 8 more zeros after the maximum energy that can be achieved with Large Hadron Collider, which is a very, very big thing. And that leaves us with a very big question, that what are some of these biggest phenomena which are actually causing these ultra high energy cosmic rays? This was my research area. That time we used to work on that maybe there are some kind of naked singularities, and near those naked singularity such high collision can be possible. But that was a very general relativistic approach with not very, very much into particle physics. That was purely GR approach. But anyway, I'll talk more about neutrinos. So what I want to say is that there are so many high energy phenomena, and these particles can emit a lot of their energy in the form of neutrinos. Now, I must inform you beforehand, these ultra high energy cosmic rays, most of them are the heavy ions, or the nucleus or the protons and all those things. And neutrinos, on the other hand, are very light. But these heavy ions, these nuclei, can create neutrinos, which can give the understanding about these ultra high energy cosmic rays. That means they are excellent messenger about such events. They can help us to understand some of the most bizarre phenomena that are happening in the universe. And it is for that reason they are such an important thing for us. They can revolutionize astronomy. There is something also known as multi-messenger astronomy. That means using astronomy from different mode of sources, like gravitational wave, neutrino astronomy, and obviously electromagnetic wave. That is something that we have been doing for a large amount of time. If we combine all these things, it is known as multi-messenger astronomy. And with the help of neutrino astronomy, we can actually understand things in a very detailed way. So a single star that can be as bright as galaxy during the supernova, we can understand a lot about them with the help of neutrinos. Now, there's something that I have so far I have talked about the neutrino astronomy, right? But I want to talk about very interesting thing, that is neutrino-less double beta decay. What exactly is double beta decay? What exactly is neutrino-less double beta decay? Why is it important? Let me first give you the context. So the thing is that we know that there is so much amount of matter that we can see, but hardly we can see any antimatter. This is a very big problem, because if we talk about symmetry, there should be equal number of matter and antimatter in the universe. So why is it the case that there is so much large amount of matter than the antimatter? One possible source is that neutrino is its own Majorana particle. Majorana means it can change itself into its own antiparticle. Now, here's the interesting thing. Neutrino itself can shift into three flavors, and these three flavors can itself be shifted into three anti-flavors. So just think about it. One single electron can be converted into six different kind of particles. That's very bizarre to think about. But how can we say that this happened? So this very well explained why there is so much more matter than the antimatter. But so far, unfortunately, we have not been able to detect neutrino-less double beta decay. There are some experiments like Calmland experiment in Japan that are trying to see this neutrino-less double beta decay. So far, they have not found any evidence. But let me tell you how this works. So what happens in beta decay is that, so you don't have to be worried about this UDD, UDU. They are just quarks. Just assume that this is just neutron which are being converted into a proton. So what happened is that, let's say when a neutron get converted into a proton, we call it as beta decay. Now double beta decay, obviously when this process happened twice, we call it as double beta decay. But why this process will happen twice? So let's say a very unstable nucleus go through beta decay and convert into a daughter atom, but it turns out that daughter atom is even more unstable. So it had to go through that beta decay again to convert into a more stable nuclei. In that case, double beta decay is happening. Now, if the Majorana nature is true, then what should happen is that in certain cases, during this double beta decay, two neutrinos which are being produced, one of them should be converted into its own antiparticle because of the Majorana nature. And if it is being converted into its own antiparticle, when they collide, it will create a small tiny amount of peak in the energy. So right side, you can see the energy. Total energy of electron should be like this. But if Majorana nature does exist, there should be a small bump of energy. That is happening because of the collision of neutrino and antineutrino. And that can only be explained with the help of Majorana nature of the neutrino. And that is a very bizarre and that is a very profound thing. So I just want you to take a moment and think about it, that in the nature, there are some certain kind of particles which have this tendency to change their own flavor. And not just that, not only they can change their own flavor, but also they can switch to its own antiparticle. It is such a romanticized thing that people have given this Majorana particle also a name known as angel particle, which has no relevance to the angel. The only reason it was given to angel particle because its reference was given to the Angel and Demon movie. So that's why the name angel particle has been given to it. Similarly to Higgs boson God particle, Higgs boson do not have any relevancy to the God, but the publisher who was trying to publish it, he was initially writing the God dam, but he didn't like the name God dam. He removed the dam, and now we call it as God particle. But Higgs boson do not have any relevance to the God. Similarly, this Majorana particle do not have any relevance to the angel. But the interesting thing is the person, Ettore Majorana, who gave the concept of Majorana particle, he disappeared 1 year after giving that. No one knows what happened to him. But I'm sure that he must have died because of some natural accident, and it has nothing to do with these particles. Trust me, these are some over romanticized things that are around in the field of particle physics. But anyway, talking about the neutrino-less double beta decay again. So these neutrino-less double beta decay are very interesting to us. One more thing that I have not talked about is the mass of these neutrinos. I told you, right, that if these neutrinos are going through flavor shift, that means that they experience mass. And if they experience mass, so obviously there should be a total number of mass, and their mass do not work like the normal mass I told you earlier. So electron is a very light particle. What is the mass of electron? It's around 931 mega electron volt I'm talking about, right? 10 to the power 6 electron volt. For the neutrino, it is around 2 or 3 electron volt, or maybe zero point 0.1 electron volt. So neutrino do not have a specific mass. And here's the most bizarre thing that I find about neutrinos. Neutrinos mass can be in the superposition of three different states. They follow the Heisenberg uncertainty principle. Imagine a particle follows the mass mechanism with the help of Heisenberg uncertainty principle. So not only it can be in the superposition of three different oscillation, three different states, but it can also acquire three different mass. And we can only calculate mass by finding the difference in the two mass. But anyway, at this point, I do not want to go too much into that. I'm planning to end this slide soon. And here leaves me with the second last slide about the neutrinos. I told you that neutrinos can be their own antiparticle. I have talked a great deal about them in the slide of neutrinoless double beta decay. Here's one more thing that I want to talk about them. These particles can be excellent messenger, not only for the reason that I told you that they have good penetration power and all those things, but in reality, they can be used for the communication purpose as well. How? So few years ago, scientists from Fermi Lab, what they did is that they tried to streamline the stream of neutrinos that they are creating, and they tried to encode some message in it. And they were able to do that, although it was not a very efficient source of communication, but the mere possibilities opens a lot of doors, a new dimension of possibilities that maybe in future we might be able to communicate with other civilization and other things with the help of neutrinos, because neutrinos do not interact with other matters. Neutrinos do not penetrate other things, and if we somehow find an efficient way to detect the neutrinos, it's very highly likely that neutrinos will far exceed the capabilities of photons to communicate. Not maybe in all the perspectives, not maybe in terms of affordability, but in terms of efficiency, definitely they can. And now I have reached to the end of my slide because I plan to leave last 15 minutes or 14 or 10 minutes for the question and answers. But before that, remember I asked you that if photons are the fastest thing in the universe, how come we detect neutrinos before photons whenever supernova occurs? Answer to that question is that it happened because what happened during the case of this supernova, first of all, this neutrino get emitted from the supernova earlier only, maybe 1 or 2 hour ago, 1 or 2 hour early only. So one reason is quite obvious, because they are coming out from the sun surface early, so obviously they'll be reaching us, because they also travel almost at the speed of light, not exactly at the speed of light, but around 99.9% at the speed of light. But we also know that photon, when they travel through medium, they get slowed down. So let's say there is a lot of cloud in between, there's a lot of matter in between, photon will be disturbed, photon will get slowed down because of that. But on the other hand, neutrinos won't get slowed down there. Neutrinos will be traveling at the exact same speed because they do not interact with themselves. And it is because of those two reasons we get neutrinos before the photons. I hope that answered that question. And by this, I like to end my presentation. I hope this was not too boring. I hope this was not too technical. I have tried to keep it as simple as possible. I've tried to keep it as informative as possible. And it's time for some high in-depth question about neutrinos. So you can shoot your questions to me. I'll be happy to answer them.
Thank you so much, Kshitij, first of all, for sharing such a wonderful presentation and a lot more information, but yet put with the creative aspect, so it would become really easy to understand with the visualization and everything. So, first of all, thank you for that. Also, I could see many of your followers are here who are just because of you with the interest of the topic that we are discussing it here. So, I request if Rishabh, you can ask students, they can ask questions, they can put in the chat box, and I can then start taking the questions so that we can give a little time for the doubt. Okay, we got one. Akshay Kumar Sharma. So the reason why neutrino detected before photon.
Okay, I already answered that, but मैं एक बार थोड़ा सा अच्छे से उसको और explain कर देता हूँ. So what happened is that जब भी कोई टाइप 2 सुपरनोवा हो रहा होता है तो वो कोलैप्स हो रहा होता है, राइट? अब वो कोलैप्स हो रहा होता है तो फोटोन जो रहते हैं, फोटोन तो बन जाते हैं अंदर सरफेस में, क्योंकि वो आपस में भी इंटरेक्ट करते हैं, पूरा डेंसिटी बहुत ज़्यादा रहती है। बट न्यूट्रिनोज की तो सबसे फंडामेंटल प्रॉपर्टी यही है कि दे डू नॉट इंटरेक्ट विद दिस नॉर्मल मैटर्स। सो ऑब्वियसली वो न्यूट्रिनोज जो है वो बहुत इजीली बाहर आ जाते हैं। तो पहले तो वो सरफेस ही पहले लीव करते हैं, लाइक देन फोटॉन्स टाइप 2 सुपरनोवा में। दूसरी चीज जो मैंने समझाई थी कि जब वो न्यूट्रिनोज जा रहे होते हैं तो आसपास बहुत सारे क्लाउड्स आ सकते हैं, बहुत सारे गैसेस आ सकते हैं, बहुत सारे मैटर आ सकते हैं। न्यूट्रिनोज उनसे इंटरेक्ट नहीं करेंगे, तो वो ऑलमोस्ट 99.9% स्पीड ऑफ लाइट पे ट्रैवल करते रहेंगे। ऑन दी अदर हैंड फोटॉन्स अगर सेम टाइम पे बाहर आ भी जाते तो वो उन सब मैटर से स्लो डाउन हो जाते, बिकॉज उस स्टार से अर्थ तक आने के बीच में बहुत सारा डिस्टेंस और बहुत सारी चीजें बीच में आएंगी। सो बिकॉज ऑफ दीज टू रीजंस हम लोग न्यूट्रिनोज को पहले डिटेक्ट करते हैं। इनफैक्ट 1987 ए सुपरनोवा जो हुआ था उसमें एग्जैक्टली यही हुआ था। सो हम लोगों को जो न्यूट्रिनोज मिले थे वो न्यूट्रिनोज दैट वर कमिंग फास्टर देन दे रीच्ड आउट टू अस बिफोर द फोटॉन्स। उस टाइम वी वर नॉट वेरी प्रिपेयर्ड अबाउट दिस फिनोमिना, हम लोग की इतनी अंडरस्टैंडिंग नहीं थी। बट वो दैट वाज सच एन इंटरेस्टिंग फिनोमिना कि उसके ऊपर हर साल मोर देन लाइक 200 पीपल राइट देयर रिसर्च पेपर, अभी भी जो इवेंट 1987 में हुआ था। दैट वाज सच अ प्रोफाउंड फिनोमिना। सो रीजन आई एम टेलिंग यू दिस इज बिकॉज कि ये हम लोगों के लिए बहुत ही अच्छा अलर्ट मैकेनिज्म है। दिस कैन इन्फॉर्म अस अबाउट द इवेंट्स दैट आर गोइंग टू हैपन इन द फ्यूचर, एंड दैट्स व्हाई इट्स अ वेरी इंपॉर्टेंट थिंग। आई होप I answered your question.
So I think this was the question which many of the students would say would like to ask. So I hope Shivam, Akshay, you got the clarity and anything you wanted to like put is respect to your first question. Please feel free to ask. Abhishek, maskless body experiences the time.
Hmm. See, the whole concept about time is that a mass has to be there if we want to experience it, right? That's the holy grail of relativity. Photon, we say photon do not experience mass because it does not experience time. हम लोग जब भी relativity solve करते हैं, मैं Einstein, I'm not talking about Einstein field equation, I'm talking about very basic relativistic mass and relativistic time and all those things. Mass is a very important part of it. So from there only we know that mass is very important in order to experience time. और अगर टाइम एक्सपीरियंस हो रहा है दैट मीन्स देयर इज एंट्रोपी। एंट्रोपी व्हाई? बिकॉज हम लोग चेंज को सबसे फंडामेंटल लेवल पे वी अंडरस्टैंड इट विद द हेल्प ऑफ एंट्रोपी ओनली। दैट मीन्स इफ देयर इज सम रैंडमनेस, दैट मीन्स देयर इज सम चेंज, तो वहां पर टाइम है, और वहां पर टाइम है, सो देयर इज मास। सो जस्ट टू आंसर, मासलेस चीजें विल नेवर एक्सपीरियंस टाइम, बट इफ समथिंग इज हैव सम मास, सो इट डज एक्सपीरियंस सम मास, एंड दैट इज द केस विद द न्यूट्रिनोस। उनका मास बहुत कम होता है, 0.123 इलेक्ट्रॉन वोल्ट, फिक्स मास नहीं होता है, दैट वेरीज अ लॉट, but yes, they do have mass, and that's why they experience time. Can
Can
neutrinos
neutrinos travel up
yes,
to infinity beyond the edge of the universe?
theoretically
Satya.
yes, they can. Considering that so many large number of neutrinos are coming out, see, when we talk about infinite, right? So what happens that by default, if we see universe has homogeneous density and every matter is distributed like this, so by that logic of infinity, obviously there will be a time, doesn't matter how many neutrinos you emit, there will be a time that a certain probability will come with that a neutrino will hit a nucleus, and that time that neutrino cannot travel any further, assuming that there is no matter. So the probability of interacting with neutrino is becomes zero. In that particular case, it is possible because they will not going to lose any of their energy in between. So yes, theoretically, it is possible.
So, in connection, I think it's a really good question. If possible, can we have neutrino based observatories as well? Like, if we can create a material which can interact with neutrinos.
So it's actually a very excellent question. And the thing is that people are creating. Some scientists at the Fermi Lab, they created some of the smallest neutrino detector. They are not very efficient, but the thing is that people are working in that field. People are working in such a way that they can detect neutrino as efficient as possible. At this point, it's not possible. That's why we have to build so large like detectors all around the world. For example, Ice Cube Neutrino Observatory. Ice Cube Neutrino Observatory is 1 kilometer square in volume, and a new project is proposed, and it will be 10 kilometers square, 10 times the volume it has right now. Same goes with the Super Kamiokande detector. It was the successor of Kamiokande, and now another detector is proposed, which is Hyper Kamiokande, which is going to be even larger. So as of now, we are relying on the a sheer amount of volume to increase our probability of detecting such things.
The
Okay.
nutshell P squared. In a parallel universe, there is a possibility of having anti-neutrino which has a right-handed spin, but they don't exist. So it's contradict the possibility of its presence in the parallel universe.
Okay, what you have asked the nutshell and p squared, it's a very excellent question, and this requires me to go into a bit more detail, right? हम लोग चीजों को पार्टिकल एंटी पार्टिकल में कैसे कन्वर्ट करते हैं, सबसे बेसिक जो अंडरस्टैंडिंग है दैट इज बिकॉज ऑफ देयर चार्ज, राइट? इलेक्ट्रॉन का पॉजिटिव चार्ज है तो पॉजिट्रॉन का अपोजिट चार्ज होगा, सेम मास होगा, सो इट्स ओन एंटी पार्टिकल. दिस डज नॉट हैपन इन द केस ऑफ न्यूट्रिनो. There we talk about chirality. So what you're saying, spin would not be the right word, chirality would be the right word. So there are two kind of chirality, लेफ्ट हैंडेड कायरलिटी, राइट हैंडेड कायरलिटी, उसमें भी फिर अलग अलग टाइप के आते हैं, बिकॉज वो फिर वो स्टेरल न्यूट्रिनोस की तरफ चला जाऊंगा. आई डोंट वांट टू टॉक अबाउट दैट. बट व्हाट आई वांट टू से इज दैट कि ये सारी चीजें जो है दे कैन एग्जिस्ट इन आर यूनिवर्स ओनली. पैरेलल यूनिवर्स का मेन जो पूरा कॉन्सेप्ट आता है दैट कम्स फ्रॉम द क्वांटम मैकेनिक्स फॉर मैनीफोल्ड इंटरप्रिटेशन एंड ऑल दोस थिंग्स. yes, if we try to dig deeper into that, maybe there can be a possibility कि अगर यहाँ पर ऐसा है तो अल्टरनेटिवली उधर होना चाहिए, जो कहते हैं ना मैनिवल इंटरप्रिटेशन से आता है. बट आई डोंट सब्सक्राइब टू दैट आइडिया दैट मच. मेरा थोड़ा सा बायसनेस बोहेमियन इंटरप्रिटेशन की तरफ जो डेविड बॉम ने दिया था. सो आई विल नॉट एग्री विद दिस आइडिया दैट मच. There is a possibility, I will not completely deny that, but a good scientifically tempered person will not argue in favor of it.
Sir, on Kiran radiation topic, my question is that is it always blue, or will they occur on the radiation change depending on the difference between speed of the photon in the medium versus neutrons?
Okay, will occur radiation depending on the difference between speed of photon. See, we see that particular blue cone of light only. So you must be aware about the sonic boom, right? When a jet travel faster than the speed of sound, it create a shock wave. We call it as sonic boom. Consider a Cherenkov radiation like that only. So this is particular. There is a particular frequency of the light that are coming from, and in the visible spectrum that comes in the form of blue color only. There are other photons that are being emitted that we cannot see, but primarily what we can see is blue color only. So it's more like, for most of the time, the shock wave that is being created because it happens in a very particular region. Because even light, if light gets slowed down, it will not go slow down very tremendously, and the particle which is traveling faster than the speed of light, वो भी बहुत ज्यादा ऐसा एक्स्ट्रॉर्डिनरी स्पीड पर ट्रैवल नहीं करेगा, बस थोड़ा सा ज्यादा. तो उस पर्टिकुलर रीजन में हम लोग को ब्लू कोन ऑफ लाइट ही मिलती है. आई होप दिस आंसर योर क्वेश्चन.
We have Vivek Rovilla. Have we captured neutrinos coming from sun? If yes, share the picture. I think he discussed in the presentation as well, but if you can elaborate a little bit.
या श्योर. सो एज मैम सेड, आई हैव ऑलरेडी एक्सप्लेन दैट. मैंने एक फोटो भी दिखाई थी जिसमें बहुत छोटा सा कोर दिख रहा था, बहुत ब्लर ब्लर सा टाइप का इमेज था. सो आई विल नॉट टेक मच टाइम. यस, वी हैव कैप्चर्ड द इमेज ऑफ द sun with the help of neutrinos.
Rupesh Prasad, can neutrino pass through the black hole and come out of it after a while?
नो, ये नहीं हो सकता. उसका रीजन ये है बिकॉज सी, we have to understand one thing, that neutrinos can hardly interact with things. Neutrinos can pass through things. Neutrinos are excellent in many things, but they are still the physical particle. And जो भी physical particle होगा, that should follow the causality. Causality means that nothing can travel faster than the speed of light. एक cause and effect का rule follow करना पड़ेगा. और जो ब्लैक होल के इवेंट होराइजन के अंदर होता है वो कॉजालिटी वायलेशन हो जाता है, राइट? सो कॉजालिटी वायलेशन न्यूट्रिनोस कैन नॉट डू. दैट्स व्हाई वो ब्लैक होल के अंदर से जाके वापस नहीं आ सकते.
So, any other questions? Because we already taken the question posted on the chat. Do we have
Okay.
any other question? Rishabh, please let us know. So, even no question in the chat, no, not inside the room. So, we got thank you from the nutshell as well. So, I'm just hoping that your doubts and queries got resolved.
I hope my answer helped you a lot.
Yes, yes. So, if not, then feel free to write to us and we'll try to get clarify with Kshitij. If anything left in the during the session, I think he elaborated everything very effectively. Yes, it was a smooth session. Shivam is also saying thank you for such a smooth session, sir. So we're just assuming. Okay, one more question. What occur when photon interact with neutrinos?
Photon cannot interact with neutrinos. In the start of my slide only, I said that photons can, in neutrinos can only interact with W and Z boson. Photon is that gamma thing that was written in the standard model slide, right? So photons and neutrinos cannot interact. It is for that reason we cannot see neutrinos so easily. अगर photons से interact कर पाते तो life would have been very easy. बट बल्कि दिक्कत भी हो जाती देन वी वुड हैव डाइड बिकॉज ऑफ न्यूट्रिनोस बिकॉज इतने सारे न्यूट्रिनोस आ रहे हैं इतना सारा हमसे बॉम्बार्ड हो रहे हैं सो दैट वुड हैव बीन chaotic फॉर अस बट या दे डू नॉट इंटरेक्ट विद photons.
So I think with this we'll wrap today's on this online session. Thank you everyone for joining in, and also thank you Kshitij for sharing once again this topic on the boot camp. And the purpose of this was to like give little broader perspective related to the topic of astronomy and astrophysics. And keeping this online, I think, have made the reach maximize. So many of the students who are unable to join offline can get the benefit of topic discussing through this meeting. So thank you once again.
Thank you for
We'll
having me.
take we'll take one more question. I think just what conclusion we have drawn from sun picture.
So the conclusion is that we have actually, to be honest, there's a not lot of things that we have concluded in terms of physical property of the sun. These things are being done just to show that neutrinos can be used to understand the core of the sun. But yeah, we do have some knowledge about the total energy of the and temperature of the sun that are there. We do have the knowledge about the cyclic reaction that are happening inside the core of the sun. These are some common things that we have find out. But if we proceed in the field of solar astronomy, solar neutrino astronomy, then with the help of neutrinos हम लोगों को बहुत सारी चीजें और भी पता चलेंगी जो at this point of time we might not be aware of, बट वो धीरे धीरे हम लोग जैसे उसको एक्सपैंड करेंगे बढ़ेगा. बट एज ऑफ नाउ कंक्लूजंस आर वेरी बेसिक.
So Vivek, I think you get the clarity. So definitely, Kshitij, we look forward for more such interesting sessions. We could plan it online and probably sometime offline whenever you are traveling to Delhi to the
Definitely.
planetarium. We'll would like to host you at the planetarium so that not only the college student but school students who are interested to know about these topics and developments can get benefited of the discussion. So thank you once again. Thank you everyone. And thank you once again for joining for these sessions. So we'll wrap this session. Bye. Take care.
Thank you. Bye.